Welcome to The Explainer. Today, we're talking about a breakthrough that honestly sounds like it's straight out of sci-fi. We're going to look at how a tiny pinch of one of the most common metals on Earth could be the secret to unlocking the future of renewable energy. So let's get right into it. So take a look at this. What if fixing our biggest energy problems was really this simple? On the left, you've got this super promising battery material that just, well, it falls apart. It gets unstable, it dissolves, and its power just fades to nothing. But then look at the right. It's the exact same material, but now it's stable, it's powerful, and it lasts. So what's the secret? It's a tiny pinch of iron. You know, if we're ever going to have a truly renewable energy grid, we need better batteries. I mean, way better. We're talking huge, cheap, and super safe. And that whole search has led scientists to some really interesting materials. But yeah, there's always a but, isn't there? This one comes with one major, crippling problem.
Okay, so scientists are getting really excited about this class of materials called hexacyanoferrates. Let's just call them HCFs, way easier. And you can see why they're excited. I mean, these things check all the boxes. They're cheap, they're good for the environment, and they have this really cool open structure. It's kind of like a perfect little hotel for all the energy-carrying ions to check into.
Right, so what's the catch? Well, it's a big one. These HCFs have a fatal flaw. See, when they're made, these tiny little defects form. They're called structural vacancies. Just think of them as, oh, I don't know, missing pieces in a puzzle or little potholes all over the place. And what's worse, water molecules just rush in to fill up those empty spots. And these vacancies, these little potholes, they are a huge problem. They're basically weak spots in the whole foundation of the material. So every single time you charge and discharge the battery, those weak spots just cause the whole thing to start breaking down. It literally crumbles and dissolves into the liquid inside the battery until, poof, the battery's dead.
So how do you fix something like that? You're probably thinking it takes some kind of super complex, expensive nano-engineering, right? Well, that's what's so brilliant about this. The researchers tried something way simpler. They didn't even touch the solid material. Instead, they decided to mess with the liquid inside the battery. The experiment was actually super straightforward. They took this standard battery liquid, the electrolyte, and called that PE, for pure electrolyte. Then they made a second batch, the modified electrolyte, or ME, and the only thing they did differently, was add a tiny bit of a common iron salt. I mean, we are talking a truly minuscule amount, basically just a pinch of iron.
Okay, so how does a tiny little pinch of iron do all that? I mean, how does it make such a huge difference? This is the really cool part. It basically creates a self-repairing system inside the battery.
All right, so let's break this down. The fancy term for it is in situ remediation, which just means it fixes itself on the spot. So you've got those pesky vacancies making everything unstable. Then you add the special electrolyte with the iron ions floating around in it. Now, when the battery's being used, when it's discharging, those iron ions get pulled over to the cathode. And what do they find there? All those little potholes, so they just slot right in and patch them up. It's like having a tiny automatic road crew constantly fixing the highway inside your battery. But here's the kicker. This repair job, it does more than just plug the holes. It actually upgrades the material. The paper says it transforms it from a single redox to a double redox material. Now, what does that mean? In plain English, it means the patch isn't just a patch. It becomes a new, active, functional part of the battery. Think about it like this. The iron atoms that come in to fill the potholes don't just become dead pavement. Nope. They become new parking spots for energy. So you're not just fixing the road, you're actually adding more capacity to the parking lot. You solve the stability problem, and you get to store more energy. It's a total win-win.
Okay, so the theory sounds amazing, right? A self-repairing, self-upgrading battery. But does it actually work? Let's get to the results, because this is where you can really see the difference this little bit of iron makes. And the visual evidence is just, it's undeniable. Take a look at these microscope images. The surface of the material from the battery without the fix, it's a complete mess. It's all corroded and degraded. But then look at the one that had the iron added. It's smooth, it's stable. Heck, it looks practically brand new. This simple fix just flat out works. And it's not just the pictures, the numbers tell the same story. And it is a dramatic one. They built a full battery using this technique, and it ran for 5,000 cycles. And after all that, it still held over 80% of its capacity. That is just incredible longevity for a battery like this. And this chart really drives the point home. Okay, so after 1,000 cycles, look at the standard battery. Its capacity has faded all the way down to 30, but the one with that little bit of iron added, it's still holding strong at over 85. That's almost 3 times more energy storage capacity. Just a massive, massive improvement. Okay, so this is obviously fantastic for this one particular material, the nickel-based one. But that begs the next big question, right? Is this a one-trick pony, or could this be a universal fix for this entire family of materials?
Well, it turns out the answer is a resounding yes. The researchers went ahead and tried the exact same trick on other HCF materials, this time using copper and cobalt. And what did they find? The exact same result. In every case, the battery that would normally fade out pretty quickly was suddenly stable and holding a ton of charge, all thanks to that little bit of iron. So let's just step back. Why is this such a big deal? Well, because it's an incredibly simple, super low-cost fix for a really big problem. You get batteries that last way, way longer, you get batteries that hold more energy, and most importantly, it makes these safe, water-based batteries a much more realistic option for storing massive amounts of energy for our power grid. And that's something we absolutely need.
And all this really leaves you with a powerful idea, doesn't it? It just goes to show that sometimes the biggest, most game-changing solutions aren't the most complicated ones. Sometimes they're hiding in plain sight, in the simplest of things. Which really makes you wonder, could a simple pinch of iron, something so common, so overlooked, really be the key to unlocking our renewable energy future?